Okay, hi again, everyone. Today we're going to look at the Drude model and what it says about optical properties of metals. So let me quickly share my whiteboard with you. And I guess what I want to start out with is big picture. So far, we've been looking at the conduction electrons, and the formula that we started with was from the perspective of conduction electrons. It was about conduction electrons. For instance, the mass in that formula is the mass of the electron. So that's the perspective we took. And so where did the electromagnetic wave figure in? Well, it played sort of a supporting role as the external driver for the motion of these electrons. Okay, so we have a driver that creates a force on an oscillating force on the electrons, and the driver, being the electromagnetic wave, then transfers energy to the electrons. So a various amount of energy is being transferred into the electron system. Where is it coming from? It's coming from the electromagnetic wave. Okay, and so what we saw there was that at low frequencies, the electrons were in phase with the electric field, the oscillating electric field. They moved in phase, and therefore we saw that there was a lot of energy being transferred from the electromagnetic wave to the electrons. That energy had to be dissipated, and we get resistive heating of the wire. Okay. On the other hand, at higher frequencies, we saw that the real part of the conductivity diminished in relation to the imaginary part. So the imaginary part of the conductivity became larger and larger in comparison to the real part. And so there now we get these electrons moving pi over 2 out of phase with the electric field. And that basically means that no energy is transferred from the electromagnetic wave to the electrons. And so therefore, since no energy is transferred, the electromagnetic wave can continue unabated without attenuation in the metal. But that only happened at sufficiently high frequencies. Okay, so that was sort of the bigger picture from before. But a more detailed analysis would have to now switch things around and look at the situation from the point of view of the electromagnetic wave. So the electromagnetic wave no longer just playing a supporting role, now it's sort of starring, okay? And so that's what we want to do next. Now the electromagnetic wave, of course, is described by Maxwell's equations. The famous Maxwell equations that govern all electromagnetic phenomena. There's 4 such equations. What are they? Here they are. Now, I have to say that these are the Maxwell equations in matter. So these are not in vacuum, but in matter. And so we have not just E and B, but we also have D and H, okay, running around. But D and H are very closely related to E and B, okay? So for instance, D is epsilon times E down here. The epsilon being the permittivity of the material. This is not epsilon naught. It's not the permittivity of free space. It's a permittivity of the material. And then mu permeability. And so here are the relationships between those quantities. There's also now a subscript F appearing here, which means free, okay, as opposed to bound. So here we're talking just about the free charges and not the bound charges. And here we're just talking about the free current densities and not the bound currents. Okay, but other than that, those are the 4 Maxwell equations. Now, I'm going to say here, parenthetically, that not everyone in this course will have seen those four equations. And I'm aware of that. You really only get to get well acquainted with them in a course like Physics 312, electricity and magnetism. So if this here just doesn't make any sense to you, you've never seen it, don't worry. It's not going to be a central aspect to this course. But if you have seen them before and you're sort of roughly aware that they exist and why things are the way they are, then you know, this might be a useful lecture to you. For instance, we see here that you know, this here is basically Gauss's law, right? The D is basically the E, so now you have the divergence of E being equal to the charge density. Or in 132, we wrote it as this, Gauss's law. The electric flux from the electric field through a closed surface is equal to the charge enclosed over epsilon. And I guess we had epsilon naught here because we're not inside of a material or not inside of matter. So this here is very similar to this equation here. Okay, and this equation here, at least the first part, is basically Ampere's law, that you need a current to produce a magnetic field. And that magnetic field will be sort of a swirling magnetic field around the wire, the current carrying wire. This here, we actually wrote in 132 as right, that the magnetic field always closes in on itself. There are no magnetic monopoles. There are no magnetic charges. We only get dipoles, and so through any closed surface, the magnetic flux is zero. So there is another way of writing it using sort of the divergence. So here we have divergence, curl, divergence, curl. In any case, what I'm, I guess, trying to convince you is that even if you haven't seen Maxwell equations in this form, you have seen them in the integral form, right? So what we want to do next is we're going to start here with this last equation. And again, if this development doesn't fully make sense to you, don't worry too much. You know, I'm not going to test you on it. So we're going to start here with the last equation, okay? The del cross H, so the curl of H. And then I'm going to use the right-hand side and substitute it in, okay? And then I'm going to use Ohm's law, namely that the current density is equal to sigma times E. That's what we've been talking about lately. Okay, so that's the first term. And then the second term, I'm going to substitute in this equation here, a relationship between D and E. And so then I get that. Okay, so then, just a quick aside, we're gonna talk about electromagnetic waves. So here's a plane wave, electric field, plane wave. Then if I take a partial with respect to time of this electric field, what you see is I'm basically taking a derivative with respect to time derivative, and it pulls out front a minus I omega from the chain rule, but the rest is untouched, unchanged, right? And so we get that a first time derivative is equal to just taking a time derivative is basically the equivalent of multiplying by I times omega. Okay, and so we get now that we can write it in this fashion. So here it used to be a time derivative, but now I'm replacing it by minus I omega. All right. Okay, and so couple more steps here, okay? I want to start here with this del squared E for reasons that will become apparent. Okay, we know that that's equal to the curl of the curl, okay? Now I'm going to use one of the Maxwell equations, and so the curl of E is also equal to minus the time derivative of the magnetic field. But any time derivative is basically going to give me an extra I omega out. So instead of taking a time derivative, I can just multiply by minus I omega, and so that's what I've done here. And so then I'm left with the curl of B, okay? So that's kind of interesting. So what are we gonna do? I wanna go backwards, okay? Here's the curl of B, but it appeared here as well, okay? So that's gotta be equal to mu times the curl of H. But mu times the curl of H appears in that formula. So that's got to be equal to 1 over c squared times that parentheses times E. Okay, and so what we see then is that the Laplacian of the electric field, del squared E, is equal to, when you follow this chain from here all the way back to here, is equal to all of this. Okay, and so that's an interesting formula because it is the wave equation. Okay, that is the wave equation. It's not the wave equation in the normal form that we see it, but I want to convince you that it is a kind of wave equation. Normally we see the wave equation written like this, right? The second derivative in space is related to the second partial derivative in time. And when any quantity satisfies such an equation, then we know that waves are possible. They are a possible solution. Okay, but taking a time derivative, we said, was equivalent to multiplying by I times omega. And if I take 2 time derivatives, well, I'm going to minus omega squared. And there's still a c squared here. So this would be the normal wave equation. Del squared E is equal to minus omega squared over c squared times E. Okay, and so now what we have is something a little bit different, okay? So if you go back a slide, yeah, we do get the minus omega squared over c squared times E, but then there's this stuff sandwiched in between, right? So we have this minus omega squared over c squared times E, but there is also another factor appearing, and that's a complex number. It's not real, it's a complex number. Now what I'm going to just assert, but you can think a little bit more about it, is that if that, that number were a real number, we'd be good, okay? But the problem is the imaginary part of that number, of that complex number. The imaginary part now leads to amplitude decay. The imaginary part of that little piece in there will lead to the attenuation of the electromagnetic wave inside of a metal, so the exponential attenuation. Okay, so then we can talk a little bit about the skin depth formula. Right, so the electromagnetic wave is now going to decay away, kind of like this. All right, we have things coming here in air, no problem, the amplitude is constant, but as soon as we sort of go inside the metal, then we get this attenuation, this exponential decay, and we can introduce a skin depth. So how far does this wave sort of go inside of the metal before it sort of decays to 1 over E, its original amplitude? And so we call that the skin depth. So you could do a little bit of work, and it's outlined in my PDF notes that I've also posted on Moodle. So I want to skip some of the math here, but you can read up on it. What ends up happening is you get a fairly nice formula for the skin depth. Okay, and there's a whole bunch of constants running around under the radical here. Okay, so I want to mention a few of them. I want to mention the omega in here. So all things being equal, blue light is going to penetrate into the metal less far than red light, right? Because for blue light, omega is larger. The frequency is simply higher. So that's a typical result you see, that the higher the frequency, the less the electromagnetic wave can sort of penetrate into the substance before it's completely gone. The skin depth basically shrinks down for higher frequencies. Furthermore, the sigma naught is in the denominator here as well. So all else being equal, a material that has a greater conductivity will have a shorter skin depth. Does that make sense? That should make a lot of sense, actually, because it's precisely the electrons that are free that are attenuating the electromagnetic wave. So the more electrons I have, free electrons, the greater the conductivity of the material, and therefore also then the shorter the skin depth, because the electromagnetic wave will be immediately damped out. Okay, so that skin depth formula should make some sense. All right, so now, before we said that at sufficiently high frequencies, we get that the metal becomes transparent, and that the amplitude, therefore, of the electromagnetic wave is not attenuated. Okay, and so how could that be? Well, it must have to do with the fact that the imaginary part in that formula, in that wave equation, that was responsible for the attenuation goes away, right? So the imaginary part in what we'll call epsilon goes away at high frequencies. So now we have sort of a way of quantifying that more. We can say, if you again go through the detailed analysis, which I'm skipping here, but is in my notes that I've posted to Moodle. If you go through that analysis, you find that the cutoff value is what's called omega p, and also called the plasma frequency. And it's given by the square root of NE squared over m times epsilon. Okay, so if an electromagnetic wave has a frequency that is higher than the plasma frequency, then the metal should not be able to attenuate its amplitude, and the electromagnetic wave should just be able to pass through the metal. And so this is a second important formula for us. We get this plasma frequency. So before, we weren't quite sure where the crossover happened, okay? We had sort of only a rough idea, but now we see that it happens at the plasma frequency. So on the homework, I'm asking you to estimate the plasma frequency for a bunch of metals like sodium. And that gives us then a sense of at what point would they become transparent to electromagnetic radiation. One thing quickly, this is omega, right? Technically it is measured in radians per second. If you want frequencies in hertz, you still have to divide this by 2 pi. Okay, so again, the detailed derivations of these formulas can be found in my post-it notes, where I also relegate some of the steps to the homework assignment. All right, thank you.